Just wait for one more minute. After that, I will mm, start the session. Okay, let's start the session. So, welcome to the fourth tutorial session of operational planning of power distribution system, whose instructor is Professor Sanjeev Gangle sir from IIT Guwahati. I am Satyakram from APMRF Research Scholar here in Department of Energy Science Engineering, IIT Bombay. So we will solve the few of the problem related to the fourth assignment that will help because due date is 2 day after that. So I will try to upload the slides and videos by today itself so that you can get a feel and try to solve the questions which is given in the tutorial session, assignment basically. Okay, so without wasting time, let's start the session. So I will give the numerical. The all the questions here are the numerical based. So in that we will see the how to solve that, and also I will give the derivation how this formulas is being arrived. Okay, just you have to follow the procedure how it is actually being seen and how it is being solved. Okay, if you directly know the equation and formulas, you can try that and let me know what is the answer. Then after that I will give the detailed solution of that. Pridarshini, you can switch off your mic please. Okay, so this is the first problem. This is related to a single phase distribution feeder, which is of suppose this is a distribution feeder. Take this. So this is a distribution feeder is there. So what it is saying, this is of 5 kilometer length. Okay, and this is having the uniformly distributed load. Okay, and the current at the sending point means whatever the current which is at this sending point, it is actually 80 amps. Okay, and feeder resistance means what you can say the small r, it is actually zero point 0.6 ohms per kilometer. Okay, so considering the uniform loading, you have to calculate what is the approximate copper loss. Okay, if you know the formula, try to solve that. After that, I will give the solution. Okay. If you're not able to solve, just let me know in the chat box so that I will be directly jumping to the solution part. Okay. And somebody who is trying, okay, option D I got. Okay. Just wait for a few more minutes so that others also can get a feel. So you have to, for solving this kind of problem, you have to watch the tutorial, means a lecture of professor and see the presentation what he have given in the lecture slide section. Let's wait for one more minute, and after that, I will give the solution. Okay, let me give the solution. Okay, so just see what I am actually telling. Okay, so you will get the feel that how this question and what the things it actually saying. Okay, so it is saying that it is single phase system. That is very much obvious. We already know the difference between three phase and single phase system, and the resistance is given into the per length basis kilometer. So you already know 5 kilometer length is there, and small r is basically zero point 0.6 per kilometer. If you wanted to solve for total r, so r you multiplied by length, that is zero point 0.6 multiplied by 5, that is 3. Okay, 3 ohm. And it is saying uniform distributed, uniformly loaded. Okay, what it is trying to say that if it is a uniformly loaded system, so the current drop will be something. Suppose this length I will try to cut into the three section. Suppose I try to cut the three section, and at each point there is a load is connected. Suppose load is connected here, load is connected here, and load is connected here. Okay, so for uniform distribution means what the current you are actually trying to fit here, I, at the end of the feeder there will be no current which is going to inject from their side. Okay, because at the end it will all the current will went into the load side. Okay, that is the meaning of uniform distributed line. So suppose if you wanted to hear the zero current here going into this, so you just have to draw that key, this I by 3 went into this, then I by 3 went into this, and I by 3 went into this. Okay, so it will be like this key, this will be giving here 2 I by 3, and then I by 3 went into this, so here I by 3 went, so I by 3 went here, so here the 0 ampere will be there. Okay, so this is can be fitted into like this. Suppose I wanted to add as a x length. Okay, so whatever the current I is actually coming, suppose I is coming, so you can say that ki I is equal to 1 minus x by l. L is the total length. Okay, so suppose at the end of the length, suppose this is a l is equal to 5 kilometer is here. Okay, so 50 ampere current it is flowing here. So at the end means at the 5 kilometer length, 1 minus 5 by 5, so you will get 0 ampere. Okay, suppose you wanted to check that ki, at what distance is actually the current will be there. So it will be like that ki, in between loads are equally divided and each having the equal drop. Okay, and at the end of the section, at the end of the feeder, there will be zero current flowing. Okay, so let's try to mimic this in the mathematical equation format. So what here it is saying that, suppose here the r is already given. So what I have already told that ki this is a length, this is a feeder length. So here the IES current is coming. Okay, and the total length is L. And if you wanted to at a distance x, suppose this is a x at a distance x, you wanted that ki what current it will flow, Ix will be simply Is 1 minus x by L. Okay, so and dr means what is the total resistance, total resistance till here. Suppose then it will be rdx, because it is actually till distance x, what will be the resistance. Resistance will be such that dr is equal to r times of dx. Okay, suppose you have taken a cross section of dx here, and which you wanted to integrate, and totally you can get. Okay, What is the copper loss formula? Copper loss formula is basically I square by R. So at a distance of x, what will be the copper loss? Ix square multiplied by R. R is basically dr. Okay, the resistance change. So when you see that, what is the dp? Dp is basically the incremental power loss at a distance of dx. So it will be simply put the value of ix here. You will get is 1 minus x by l square r dx. Okay, you can simplify ix square 1 minus x by l r dx. So the total copper loss, if you wanted the till overall distance, the copper loss will be there. So it is from the 0 to l length. So you have to integrate from 0 to l. Okay, so when you see that power, so this will be dp. Dp is basically integrating from 0 to p, so that is simply p. So power is equal to simply is square 1 minus xl by x by l of whole square r dx. Okay, r is constant, is square is constant, so you can take it out. Is square r 0 to l 1 minus x by l of whole square. Then what you see when you wanted to integrate, take substitute some values. Suppose 1 minus x by r, let takes it is u. So it will be simply equal to dx minus dx is equal to l times of du, and du you can say that dx will be simply equal to minus l du. Put the value here, you will get simplified value. And also when you add x is equal to 0, u is equal to 1 minus x by l. Put the value here, you will get 1. At x is equal to l, you will get value 0. Okay, so the you wanted to integrate from the 0 to 1, u square and is square xl is constant. So you will get the power equation as power is equal to 1 by third of is square times of rl. Okay, so this is a kind of total power loss in between the overall line. Okay, when you see that this is a one third of this, so what was the question? That if you have already length is already known, is is already known, and small r means zero point 0.6 ohm per kilometer is already known. So you have just to have to put the values. 1 by 3 is square is 80, what is already given. Total length is 5 kilometer, and small r which is given per unit length value, it is zero point 0.6. When you calculate, it will come out to be 6.4 kilowatt power loss. Okay, so it will be simply option b. Okay, so here you what you have to remember here, few of the formulas here what I am given here. The derivation part is not important. You have objective question will be there. So this I have kept the derivation because it should be known. Okay, so how this value came 1 by 3 is square rl. Okay, any doubt in this? If you feel that there is a problem in understanding, just let me know, I will explain further. Okay, 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 then I assume that I have explained this. So whatever, when you see that uniformly distributed, so this point you should already remember that this formula is valid for uniform loading, that I have explained that in equal current will be delivered to the each load. Okay, so this formula will be, you have to remember that power loss in a uniformly distributed feeder will be equal to copper loss will be equal to 1 by 3 is square rl. Okay, let's move further and try to see the voltage drop part. Suppose there is a 11 kV three-phase feeder is there. Three-phase feeder is there, and total length is given as 6 kilometer, and this is also given uniformly distributed. Okay, and impedance small r is given as zero point 0.8 ohm per kilometer, and the sending it current means is is already given 100 amps. So it is asking what is the percentage voltage drop. Okay, so what will be the percentage voltage drop in this feeder? You just have to explain that. Okay, try to solve, and after that I will give the solution, also derivate what is the exact value will be there. Okay, I am also solving with you. Try to solve and uh, let me know. Let me bring calculator. Anyone who have got the answer? 1000 multiplied by 100, that is 2 so it is there. Okay. Okay, I got one answer at option A. Okay. Let's wait for 30 more seconds. After that, I will give the solution. Yeah. Okay, let me give the solution. So, first let me explain. Okay, and after that, we will see that whether it is correct or not. Okay, so this is from the average. It is being solved. Okay, okay. Let me explain. Okay, so when you see here, so let me erase this. So this is a uniformly distributed feeder is there whose length is L. Okay, current flowing at the source end is the IS. Okay, and the resistance is R is basically equal to zero point 0.8 ohm per kilometer. Okay, it is already given. Okay, suppose at a distance x. Okay, so a small distance means x plus dx. Suppose this is the x plus dx length. Okay, we wanted to find it out what is the current flowing here. Okay, so this we have already known that ki is when you wanted to find out at a particular ix, basically I at a particular distance x, that is equal to 1 minus x by l. Okay, so this is the current which is flowing across the distance x. Okay, suppose if I wanted to see that ki what is the current flowing at a x plus dx distance, so it will be simply equal to ix 1 minus x plus dx divided by l. Okay, and we wanted to find out because the voltage drop is basically when you wanted to see that is I uh, uh, multiplied by dx distance. Okay, in overall system, so whatever the current will flow and the till the dx distance, so till dx distance the current voltage drop in between the line, that is delta v till distance dx is equal to I dx. Okay, or you can say that voltage at x minus voltage at x plus dx is simply equal to I times of dx. Okay, so let's subtract that ki what is the current actually flowing into that. When you try to solve it, let's take a difference of this. So that is I dx, or you can say that ki voltage is here. Okay, so this is a current value at a particular distance what we have seen. Okay, let's try to see that what is the voltage will be the drop in between the line. Let's take a new slide. Insert. Let's take a new slide. Okay. So what I have explained that ki voltage at a particular distance x, you have to find it out. So it will be simply equal to voltage at this and x plus dx. Okay. So the voltage which is there at a distance of x will be the I multiplied by basically voltage will be simply equal to the at a distance of x will be simply equal to I into multiplied by resistance, voltage into current into resistance. Okay. So when you see that what is the current voltage drop will be there in between here, so it will be simply delta V when you wanted to find it out. So it will be from starting from, suppose I wanted to find out from 0 to here x distance, what is the voltage drop will be there. So simply here is the voltage which is there at a maximum when you can say, and also at a voltage will be there at a particular distance x. So V max minus Vs will be simply equal to delta V. Okay. So the current which is flowing at a source end, that is the Is will be there, minus at a distance of x the current will be 1 minus x by L, that I have already shown you. Okay. So when you take the difference of that, so it will be come out to be Is x by L. Okay. Why? Because at a source in the voltage will be maximum, and as you move on towards the end side, suppose this is the end side, the voltage keep on decreasing. Okay. So the V max will be there at a source end, and this is at a distance of x, that is a Vx. And when you wanted to find out, so just multiplied by the current, subtract the current which is there, and then find it out multiplied by the Z. Okay. So this is a current drop and multiply it by the RDX, because it is a uniform distributed line is there. So this will be the RDX. Okay. But we wanted to find it out that what is the voltage drop across the line. Okay. So delta V will be simply equal to Is x by L RDX. Let's take it from the 0 to L distance. Okay. This is equal to 0 to V and 0 to L. Okay. So this is Is R by L. You can take it common. 0 to L, simply x dx will be there. Okay. Try to solve Is R by L. It will be simply equal to x square by 2, 0 to L. Okay. So when you try to solve Is R by L multiplied by L square by 2. Okay. So when you get that, delta V will be equal to half times of, you can cut L here. So it will be simply equal to half times of Is multiplied by R multiplied by L. Okay. Try to fit in the value delta V is equal to half multiplied by Is. Is what is already given here, that is 100 ampere, multiplied by resistance is already given, that is equal to zero point 0.8, and the total length is given. Total length is what the total length is given, that is 6 kilometer. Okay. When you try to solve, this will be 2 3, and it will come out to be 240 basically. So 8 here 24. Okay. So it will come out to be 10 uh, 800 ampere, so it will be 8 3 are 24 multiplied by 10. Okay, that's fine. So 240 volt is the voltage drop. So what it is saying that when you have this at a from starting point till the length L, the voltage drop in between the line, what happened, it is the 240 volt. Okay, so in the question it is asking what is the percentage voltage drop. Okay, percentage drop will be simply what was the voltage drop to 240 and divided by what is the total voltage. Total voltage is basically 11 kV. Okay, multiplied by 100. Okay, so when you try to solve it, it will come out to be nearly it will come out to be 2.18%. Okay, but here there is a twist. There is a twist here that what you got the 2.18, this is not for a, this is for a single line. Okay, so because the feeder which is being said, it is actually three phase feeder line. Okay, but what we have derived, it is actually is a single phase feeder. So for getting the three phase feeder value, so it will be higher than that. Okay, so 2.18 voltage drop in the one feeder line. So what will be there in the three phase system? Okay, so for three phase system, there is a different derivation is there. Okay, that derivation, are you getting my point? Because what I have currently derived, that is voltage drop in between the line, this is for a single line. But feeder, what is being asked, it is a three phase, because three phase having the three wires, and the each feeder will have the voltage drop. Okay, so let's try to follow for the three phase feeder. Okay, for the three phase feeder, basically, the voltage drop will be, that is formula will be the same. But only the thing is, what is the voltage which will be derived? That is actually the root 3 times of I average times of Z total. Okay. And the average drop current will be simply equal to the half. Okay. So I'm not going into derivation, but I'm just trying to correlate with the system. Okay. So it will be half times of I. Okay, so and the voltage drop equation will be simply like this, root 3 I average Z total. Okay, when you try to solve it, it will come out to 415.7. When you put the value, it will come out to be 3.78. Okay, so but in the option 3.78 is not given, so approximate value when you say it is closer to the 4, so it will come out to be 4.36. Okay, so the option B. So the answer which I have got, one of the answer I have got in the comment section is option A, basically from the Kanchan and from the Srinidhi, that is A. So that is being derived, that is closely related for the single phase system what we have derived. Okay, but when you see the three phase system, it is very different. Okay, then you have to use the average formula. Okay, then you will get the 4 point something voltage drop, that will be nearly equal to 4.36. Okay, try to remember. Okay, there is a difference between the voltage drop in the single phase line and the three phase line. Okay, this is another question that is similar kind of, that ki distributed load is there. You have to find out what is the total feeder power loss, what is the approximate feeder power loss will be there. I have already given you some glimpse. You just have to keep the values into the equation and try to find out. Okay, option A. This I have explained that it in the first question. Just I have kept it to give a glimpse and to remember the formula. Anyone else? Okay, let me give the solution. So, in the derivation part, we have already seen that what is the value of the power loss. That will be equal to power is equal to 1 by 3 times of is square RL. So, in this problem, we have already seen when you have a feeder that is single phase, here it is not given, assume that it is single phase, and 1 ohm per kilometer small r is given, L is given 4 kilometer, and is is already given 60 amps. Power loss means basically the copper loss will be equal to 1 by 3 times of is square rl. Okay, so it will be 1 by 3 60 square multiplied by 1 multiplied by 4. It is simply, when you solve, it is 36 multiplied by 4 divided by 3. It is simply coming out to be 4.8 kilowatt. Okay, this is very easy. You just have to remember the formula that when you have a uniformly distributed line, and the copper loss will be 4.8 kilowatt. Okay, now try to solve this. Okay, so that is easy enough to solve that, because it is already, we know, is square rl. Okay, so it will be 1 by 3 120 of square multiplied by r is zero point 0.5 multiplied by 10. Okay, so it will be simply equal to 120 of square 20 of square multiplied by zero point 0.5 multiplied by 10 divided by 2. It is coming out to be 36 kilo. Okay, 1 by 20 divided by 3, that is come out to be 12. Okay, 120 of 120 of 20 of square multiplied by zero point 0.5 multiplied by 10 divided by 3. It is coming out to be 24 kilowatt. Okay, 24 kilowatt is the answer. Option B is actually correct. Okay, Oof. Try to solve this. Hmm. Let's wait for 10 more seconds. After that, I will give the solution. Okay, let me give the solution. Okay. So here you just have to remember few things. Like first thing here, that what is given here, that is three phase feeder is already given, and line to line voltage, that is 11 kV is given. Okay, and the length is given 5 kilometer, and the impedance per kilometer, that is small r, is given as 1 ohm per kilometer. Okay, and the I from the sending it is given 90 amps at a zero point 0.9 for power factor. Okay, since only the magnitude of feeder impedance provided, so no separate R and X value, so you have to take the lump value. Okay, that is whatever it is given, you just have to lump that. That is given as Z. Okay, not R, not X, that is simply Z total. Okay, so what is the voltage drop? So what I have given in the previous question, let me show you there in this. If you remember here, what I have shown that what is the voltage drop will be there, root 3 I average Z total. Okay, so let put the value here also. So simply where it went. Okay, so what is given here, delta V by L. Here, so it is given delta VL is equal to root 3 times of IZ. So that is simply, you have to remember that voltage drop in the line to line will be equal to root 3 IZ. You just have to put the mod of Z is the Z multiplied by capital L. Okay, you just have to put the value. When you putting the put the value, it will be root 3 multiplied by 90 multiplied by 5, because it is 1 ohm per kilometer, so 5 kilometer length, that is be 5, and then simply it will be equal to 1.73 multiplied for 50, which is come out to be 779.4. And when you see the percentage voltage drop, so it will be simply, what is the line to line, 11,000, and what is the voltage drop came in the line to line is the 779.4, so it will come out to be multiplied by 100, nearly 7.1%. Okay, so when you see the options, it is actually option D is closed. Okay, so you just have to remember that when I say single phase line is there, so it will be 1 by 2 multiplied by IS multiplied by R multiplied by L. That is voltage drop. But when I say that it is a three phase line, you just have to remember it is root 3 multiplied by IS multiplied by R multiplied by L. Okay. So this is the for the three phase, and this is for the single phase feeder. In case of uniformly distributed feeder. Okay, let's move forward, try to solve this. This here, one thing given which is new here, it is given as a triangular service area. Okay, if you already know this way to solve this kind of question, you can directly jump in, and if you don't know, I will give them to time to solve, and if you don't know, just wait for a few more minutes and try to see and read the statement what is given, then after that I will give the solution. Okay, I think most of people are not able to understand. Let me give you solution for this. Okay, so what I mean to say, when you see here estimated feeder power loss. Okay, so triangular service area means, so it is simply like this. So when you have a service means here, and there is a this kind of a structure is there. Okay, so in that the feeding will be something like this. So let me explain your side. So it can be like this. Okay, so the feeding will be something from this side, uniformly distributed from here in. Okay, so this kind of a structure is mainly a kind of very prominent in a triangular feeder, or you can say hexagon structure feeder. Okay, so these kind of prominent feeder structures are there. You have seen in the lecture videos as well. So in this type of problem, what will come in the exam and whatever the come into the derivation you see from the lecture videos. But only thing you have to remember that what is the in a kind of triangular structure and in a case of hexagon structure, what is the power loss formula and the voltage drop formula. That is only thing which is very very important. Okay, else you can skip that other parts. Only thing you just have to know that what is the power loss formula is there, what is the actually one second. Okay, so you just have to remember the power loss and voltage drop formula. Okay, so in this case that is simply when you say the copper loss, that is 1 by 3 is square r loss will be there. So you just have to put the value in this and you will get the answer. So it is simply is square means 1 by 3 times of is square r, just what I have already told in the single phase feeder, which is simply applicable in that. You just have to put the values in this and just you have to remember. Okay, derivation part is not one time you can see, but multiple times it is not required. Only thing you just have to remember the power loss and voltage drop formula for a triangular feeder and the hexagon feeder. You can directly solve that. Okay, in case of uniformly distributed line and in case of with this non-uniform distributed line as well. Okay, you just have to put the value in this and you can get the answer. Moving forward, this is try to solve that we have already seen. I just wanted that you have get the glimpse of that. Okay, there is a three-phase feeder is there, 11 kV, and length is given, impedance is given, sending in current is given. Just try to find out the approximate voltage drop. Formula I have already given here just to remember the concept and try just apply the values and you can get the answer. Okay. Any answer? So the value is already seen. Na? The what is the voltage drop will be there, root 3 I multiplied by Z. Okay, root 3 is already I is already given 1.8, total Z is zero point 0.7 multiplied by 8. You can get the approximate voltage drop. What will approximate voltage drop? That is equal to root 3, that is 1.732 multiplied by 110 multiplied by zero point 0.7 multiplied by 8. You will get nearly equal to 1066.912 volt, and percentage voltage drop will be this value, 1066.912 divided by 11,000 multiplied by 100. Okay, divided by 11,000 multiplied by 100, that is simply coming out to be 9.6992. Okay, which is not matching. You can say the option D is actually correct. Okay, so this kind of formula will be, you have to remember voltage drop and the power loss. Let's move forward. This is already we have solved. Approximate figure. This you have shown. Okay, you have uniformly distributed, that is equal to 1 by 3 is square error. When you have the triangular feeder, also in this case also you have, suppose here the triangular loading, here it is given, approximate power loss is being asked. Okay, in this the formula is simply equal to 1 by 5 times of is square rl. Okay, but in that case there is a simple formula is there, which is in the angle terms. Okay, the power loss, delta vdn, this is for the power law. Delta Vn is equal to K times of 2 by 3 multiplied by D multiplied by In cube tan 360 by degree by 2n. Okay, I'm not going it. I'm just giving the glimpse that there is a formula which is angle based. Suppose you have a service means here and you have a triangular structure, or you can say that a hexagonal structure is there. How the service means is actually connected. You just have to see the branch angle. Okay, that theta value. After that you can, and this is formula value when you have the more than three kind of structure feeder loading structure is there, like triangular hexagon is there. Okay, let's move forward. Try to solve this. Let me move to the good question. Okay, this kind of problem is also there when you have a distributed substation, and it is been seen that how many number of identical feeders are there. There is a square service area will be there, like this survey mains is there, and you have a squares, four identical feeder is there. Suppose this is you one feeder is there, and you have a second feeder is there, you have a third feeder, fourth feeder. Okay, this is identical feeder is there, and area is given, area is 3 kilometer square, and there is a load density is given, load density rho is given. So our delta you can say is equal to 700 kVA per meter kilometer cube. Okay, so in this question the total substation capacity has been can be asked. Okay, there is a formula you can directly put in, and I will give the solution. This is kilometer square. This is another type of question. If you know the formula, just try to fit in and get the answer. Otherwise, I will give the directly the formula. You just have to remember, try to see the slide, what is already given. Just write the column wise. If you have a uniformly distributed, you have a non-uniformly distributed. When you have a triangular shaped feeder hexagon, just try to write the power loss and the voltage drop formula. That is mostly important, the formula value. And remembering that this is a uniformly, this is non-uniformly. Okay, I will add that in the slide, my slide, and upload that. But from your side, just this kind of problem will be there. Okay, option C I've got. Let us check. Okay, that is correct. Okay, you just have to remember that option C. Okay, what you guys have wrote, option C. That's true. So you just have to remember one formula, that is SF is equal to delta times of AF. That is simply, you already know the units are 3 kilometers square here, and delta is given 700 kVA per kilometer square. So you just have to multiply it. So 700 multiplied by 3. Okay, and it is asked for the 4 feeder, that is n times of, you have to multiply, so that is coming out to 8400 kVA. Okay, that's true. Let's move forward, try to solve this. Here directly the area is not given. Okay, option C I got. Let's wait for a few more seconds. Okay, let me give the solution. So when you see here, the same kind of problem is there. Only the area is not being mentioned. Okay. So area you already know, that is length multiplied by width. Width will be there. So it is simply 10 multiplied by 1, that is 10 kilometer. And what the formula was already there, that is actually here also. But here when you see the previous problem, here it is being mentioned that four identical feeders are there, but here you can say the A feeder is there. Okay, you don't have to multiply it by 4. Okay, so simply the area is given, that is 10, what you have calculated length multiply, and delta is already given 600 kVA, that is simply equal to 6000. That is option C is actually correct. Okay, try to solve this. So here it is given the k constant the value, and it is 0.0005% VD per kVA kilometer, and the total served area, S is given as 4000 kVA, and length is already given 8 kilometer. It is being asked what is the voltage drop. percentage voltage drop. Okay, option D. Okay, let's wait for 1 more minute. Okay, let me explain. So the percentage VD formula, that is simply equal to you just have to remember that when you have the kVA kilometer loading, it is already given K factor, that is 0.0005% VD per kilometer, and the total load is already given 4000 kVA. And when you have this kVA per kilometer effective, that is being asked, what is the, in the question itself, what is being asked, that is percentage voltage drop. Okay, percentage VD is simply equal to K multiplied by kVA kilometer. Okay, effective. Okay, and this K, that is already we have already given here, and the kVA kilometer effective is S multiplied by L by 2. Okay, this is the formula, and the S is already given, that is 4000, and length is already given 8 kilometer, 8 by 2, and the K value is already given, that is 0.0005, and it is in the already in the percentage. When you multiply it, it will become 416 multiplied by 5, that is nearly equal to 8%. Okay, so the correct answer is actually C, that is 8%. Okay, so you just have to remember, and multiplying L by 2, S multiplied by L by 2, not L. So that's why you got, I think, incorrect answer. So it is K value multiplied by S multiplied by L by 2. Okay. Try to solve this. That is easy, I think. But there is a question here, is the 6 triangular service feeder is there. Okay, option C. That simply we already know that key yes is already given, load density is given, that is delta, and it is given of the length is already given, that area is already given, that is 2 kilometers square, and it will be n multiplied by area multiplied by density, that is 6. Six triangular areas is there. Okay, 6 multiplied by 9,000, so that is simply 6 multiplied by SF. Okay, so 9, so what, 600 multiplied by 2 multiplied by 900, so it will come out to be 18 multiplied by 6, that is 10800 kVA. Okay, option C. Let's move forward. This is a different kind of question. Here you just have to tell me the maximum loading it can carry. Okay, option B, I got one answer. Option C also. Okay, let me explain. So it is saying the feeder current is already given, that is 180 ampere, and the voltage line to line is given, that is three phase, that is 11 kV kilovolt. And what is asking, what is the maximum loading? Okay, so the power you already know. Power is actually root 3 VL, V line to line, VL IL cos phi. Okay. Okay. So the loading is basically, percentage loading is basically the how much power you can give from this feeder. Okay. So the maximum it is asking. So P max it is asking. Okay. So this is actually constant. When you say the V, it is constant. It is already given here. The 11 kV. It is given 11 kV here, and the IL is also constant. What is you can give 180 amps, and the cos phi is variable depending upon the loading condition. So it is asking P max, so the cos phi should be maximum. So it will take the 1 here. So it will be simply root 3 multiplied by line to line voltage 11 and multiplied by 180. It is multiplied with you can say that VA kVA. How much it will come out to be? It will be root 303 multiplied by 11 multiplied by 180. It will come out to be 3429, or you can say 3429 kV or 3.429 MVA. That is simply equal to option B. Okay. So here one more thing. This is power factor unity. This is come out to be megawatt. Okay. But when you have the power factor is equal to 1 or maximum loading is being defined, you always take the S value, root 3 VLIL. Okay. So S is actually already maximum, and S is simply equal to P square plus Q square. Okay. So the Q here we are assuming that it is 0. So that's why S is equal to P. Okay, so the all the power which is generated, it is equal to S because it's a unity power factor. But when the power factor is different, suppose it's zero point 0.8, so there will be some reactive component will be there, so there will be drop in P. Okay, so the S is maximum capacity it can, maximum loading it can carry. Okay, let's move forward. This is also a similar kind of problem, but here it is power factor is given. So okay, try to solve this. The formula I have already given. You just have to put the value in that and let me the answer. Let's wait for one more minute. After that, I will give the solution. Okay, let me give the solution. So we already know what is the voltage drop in this case. That is, we root 3 IZ. That is not depending upon the maximum loading. Power factor is not considered here. So that is simply equal to root 3 multiplied by current, that is 130 amps. And what is the Z value? 6 multiplied by 1.1. So that is simply the voltage drop. So nearly. So when you find it out, it will come out to be root 3 multiplied by 130 multiplied by 6 multiplied by 1. That is come out to be 1486.099593. Okay, volt. So percentage voltage drop will be simply equal to 1486.1 divided by 11,000. Okay, multiplied by 100 divided by 11,000 multiplied by 100, 13.5%. So no, okay, so it is uniformly loading the voltage. So here the options are not matching. Here impedance is this, length is this, so that is similar problem. Here the answer I think L by 2 they have taken. So I will revise the solution. So it is simply equal to 11.5. That is not matching in the problem. So that is 13.5 would be there. Okay. This question, this type of question we have already seen. That is a feeder length. That is also we have seen. That is area and delta is given. 6 to 12 load density, voltage drop. Okay, this kind of problem will be there. So try to solve this. So this is kind of when you change the feeder length from suppose you are changing from 6 kilometer to 12 kilometer. What will be the with the same loading, such a density delta and k? So what will be the voltage drop? How the voltage drop will change? 8 times it is being said. So what was the formula initially I have told? Hmm. 8 times? It is between the double means cubic term times. Re-verify. Okay. Okay, let me explain this. So it will simply become a square. Means ki delta percentage voltage drop will be proportional to length of a square because the current was uniformly distributed. That is why it is vary with the square term. It will become 4 times. Okay. Because half I square RL, that is the power loss will be there. So when you have the load density constant, means uniform distribution is there and K is also constant. So the current is square. How the current will vary, the voltage drop will vary in that sense. Okay. So that's why the IS square term is there. So that is the lengthwise variation will be there. So that's why 4 times. Okay. So this few of the problems, that is similar kind of problem, that number of feeders and all I have kept here, that is similar. So that's all for today's session, and I will put some of the values, that is formulas and all, in this, and upload the slide and the video of this, and try to solve the current assignment, which is due, I think, after 2 days. You have to submit it, and let me know if you feel any problem in understanding any concept in the next coming tutorial session. Okay, that's all for today. uh, Thank you so much for joining.